Today we're going to finish up graphing trig functions. We don't do as much graphing by hand. We'll do a little, but most of the graphing we're going to do with tangent, cotangent, secant, cosecant will be on the calculator. So let's start by graphing tangent, and we're going to use what we already know about sine and cosine to help us out. We know that tangent can be written as a fraction. This kind of touches on the last question that was in the homework. Does anybody remember what two trig functions you can use as a fraction to write tangent? Yeah?
Sine over cosine.
Right, sine over cosine. So now, when is a fraction equal to 0? What has to happen for a fraction to come up to 0? Yeah?
For its numerator to equal 0.
Right, the numerator has to equal 0. So that means that tangent will be 0 whenever the numerator of that fraction is 0. So we just have to think about what we know about sine and figure out when is sine 0. And when that's 0, that's when the graph of tangent will also be 0. And when it's 0, that means it's crossing which axis? Yeah. No, not the y-axis, the x-axis. Okay, so when the graph is 0, we're talking about the roots of the graph, okay, which is the x-intercepts. Okay. So the graph of tangent will have x-intercepts whenever sine has x-intercepts. Or we could also say the graph of tangent is 0 whenever the sine is 0. Okay, so we'll figure that out in a minute. Now, what would happen if cosine was 0? Well, first of all, is cosine ever 0? Okay, Marcel?
Yeah.
Yeah. That basically, I'm asking, does cosine ever cross the x-axis? Sure. Yeah, it does cross the x-axis. So what would happen if cosine came out to 0 in that fraction? Yeah, that's it would become undefined. And what do you think that would look like graphically if something is undefined? There's a couple things it could look like.
Maybe it could look like, I don't know, a section of the graph disappearing as it reaches 0.
Okay, yeah.
An open circle.
Okay, so we could have a hole there. We've talked about having a hole in the graph. That could be an undefined value. And what's another way we could have an undefined value besides a hole? Yeah?
Vertical asymptote.
Vertical asymptote. And that's what's going to happen here. All right? So anytime that the cosine comes out to 0, you end up with 0 in the bottom of a fraction. If 0's in the bottom of a fraction, then that's going to equal undefined. And then what we can do is, if we know we have a vertical asymptote, we can test the behavior on each side. And usually, as you approach a vertical asymptote, what happens to your y value? One of two things. Yeah?
It goes like either really high up or it increases really fast. I don't know how to explain it, but
All right. So you're basically right. Can anybody just explain it a little more formally?
oh wait,
Yeah?
would you say that it reaches infinity?
Yes. As you're approaching a vertical asymptote, your y value approaches infinity, or it approaches negative infinity. So let's think a little bit about some of these values. Okay, here's the graph of sine. Here's the graph of cosine. Just in the first, just what you can see on the screen there, Where does sine cross the x-axis? In radians. What values does it cross the x-axis at? Yep. Pi. Yep. Where else on that you can see there? 2 pi. And where else?
0.
Yeah, 0. So this crosses the x-axis at 0, pi, 2 pi, 3 pi, 4 pi, 5 pi. Every integer multiple of pi, it's going to cross the x-axis. Okay. Let's look at cosine. Where does cosine cross the x-axis? Yep.
Pi over 2.
Pi over 2. And what's this one?
3 pi over 2.
3 pi over 2. Next one would be 5 pi over 2, 7 pi over 2, 9 pi over 2. It's every odd multiple of pi over 2. So now we can use that to help us graph tangent. Right? Tangent is going to be a periodic type of graph, meaning it is going to have a pattern and it repeats itself, but it doesn't look like a wave. Okay? So let's start to make a graph. Okay, what I've done now is I've written down some of the asymptotes. Okay, pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2. I just wrote down the first 3 positive ones. And then I also labeled my x-axis like we always do, pi over 2, pi, and so on. And now, everywhere that cosine is 0, I'm going to get a vertical asymptote. So I'm going to draw some vertical asymptotes at those values. Pi over 2 and 3 pi over 2. Okay, what I'm setting up right now is one section of the tangent function. Well, what one cycle of it is going to look like. If I wanted to do a second cycle, I could add in an asymptote over there, and then I could have 2 sections. Okay, but I'm just going to focus on the section that's between asymptotes 1 and 2. Okay, so now we know that it's going to cross the x-axis whenever sine is 0. Okay? These are the values when sine is 0. 0, pi, 2 pi. Okay, so let's mark where it's going to cross the x-axis. 0, it's going to cross at 0, but I'm not looking at that section right now. Pi, I'll look at that section. 2 pi, also going to look at that section. Now, we want to figure out what happens as we get close to the asymptote. So if we put tangent in, let's do tangent x, and we go to our table. What I can do is put in a value very close to pi over 2. So if you want to put in a value that's very close to it, all you have to do is take pi over 2. This is set up so I can type. Yes, okay. So take pi over 2. And I want to put in a value that's a little bit bigger than pi over 2. I want to look to the right of asymptote 1 and see what's happening to my curve. So go like that. Pi over 2 plus 0.001. That's a value that's a little bit bigger than pi over 2. And I'm at negative 1,000. So when we are just to the right of the asymptote, my y value is going to negative infinity. So way down there. What do you think is going to happen just to the left of asymptote 2? Where do you think my y value will be for that one? Yeah?
Would your y value approach positive?
Yep, it's going to approach positive infinity. So if we want to check that, let's put in 3 pi over 2. But I don't want to type that in, I'll get an error, because that's an asymptote. Let's put in a value a little bit smaller. So we'll do minus 0.001. And we're at positive 1,000. Okay, so we're way up at the top. Okay, so this graph has a curve to it. So it's not linear, even though it kind of looks like it might be straight. It looks something like this. Okay, so the graph of sine and cosine really helped us to figure out the graph of tangent because it gave us the asymptotes. We looked at the behavior near each asymptote, and we were able to figure out the x-intercept, again, based on what we already knew about sine. And if you copy and paste that, you would get a second cycle of tangent. Now you're looking at 2 cycles. That's what the graph of tangent looks like. Okay. Any questions on that graph? So now, just to make sure we kind of understand, if I put a box, like right there, I just put a box around one cycle of tangent. Now, that box, we can't say that that box has 2 asymptotes in it. Because if I put another box, each asymptote can only belong to one box. So if you say that, let's call this one box 1, that's box 2. If you say box 1 has both of these asymptotes in it, then what does box 2 have? Okay. You can't say that asymptotes 2 and 3 both belong to box 2 because you already said asymptote 2 is in the first box. So the idea here is there is only one asymptote per cycle. Another way to think of it is I kind of imagine like, in a movie theater, we got armrests on each side. You can't say that you take both and then everybody can take both because then there's not enough armrests that way. It has to kind of agree like, all right, we'll just take the one on the left and then everybody will always have one available like on the left, like if you're in the middle. Okay. So the idea here, I just think of asymptote 1 as belonging to the first box. Asymptote 2 belongs to the second box. So there's only one asymptote per period. Any questions on that? All right, so now we just looked at tangent. What's the connection between tangent and cotangent? Yeah.
They're both reciprocals.
Yeah, they're reciprocals. So if we graph cotangent, it's going to be cosine over sine. So what does that mean is going to happen when we try to graph cotangent compared to what we just did with tangent? Yep.
Would it be like a flip of the graph?
Okay, so you think it might flip? What's going to happen in terms of just that information you can see right there? How is that? How are the zeros and asymptotes going to change?
Well, I guess there would be a vertical asymptote when sin of x is 0.
Yep, so we're going to have vertical asymptotes when sine is 0. Yep.
So maybe the points at which you see that graph of sine of x, maybe the point at which sine of x crosses the x-axis are going to be where the asymptotes are.
Yep, so the sine is where the asymptotes are going to be. And what about with cosine? What's that going to tell us?
When cosine is 0, tangent is 0.
Right, when cosine is 0, cosine is 0. The tangent will be 0. So all the zeros and the asymptotes are going to switch between tangent and cotangent. Okay, so remember, cotangent is just the reciprocal of tangent. And if I put the two graphs next to each other, I think I already have the other one. You can see the difference with cotangent. First of all, it does curve the other way. You can check that out by examining the behavior and using the table. But what you can see a little easier is that at pi over 2, we had an asymptote when we did tangent. But now at pi over 2, we have a root, and that's cotangent. At pi, we had a 0. That's where it crossed the axis. But now, pi is an asymptote. So everything switches places in terms of the asymptotes and the roots between tangent and cotangent. It's the same idea that you can only have one asymptote per cycle. And because the asymptotes repeat regularly, you don't have to memorize all the asymptotes. All you have to do is memorize where one asymptote is, and then you can figure out where they all are because they repeat every cycle. Now, let's see if we can figure out the length of a cycle for tangent and cotangent. What is the length of a cycle for sine or cosine if you don't modify it at all? What is the length of one period? Yep.
2 pi.
It's normally 2 pi. Yep. You can modify it, but if you don't, it's 2 pi. Right? Let's look at tangent and cotangent. These are tangent and cotangent unmodified. We haven't done any transformations to them. Anybody think they can look at the picture and figure out the length of the cycle of tangent? Yeah,
Is it pi?
it's pi. Yeah. Why did you say that? Why not 2 pi?
Like the box is like just 2 of the grids instead of like 4 of them. So
Yeah, so if you look here, if you travel from pi over 2 to 3 pi over 2, that distance from here to there, that is one cycle. Right? Well, pi over 2 is 90. 3 pi over 2 is 270. What's the difference between 3 pi over 2 and pi over 2? That's 180 degrees. 270 to 90 is a difference of 180, right? Which is pi. Okay, so tangent and cotangent have a naturally faster cycle than sine and cosine. The normal period for tangent and cotangent is pi. Okay, any question? So that means when we modify it and I ask you to find the new cycle, you can't use the formula 2 pi over b anymore. We have to change it to work for tangent and cotangent. And instead of 2 pi over b, it will be 1 pi over b. That's how we modify it. Okay, that's what I was just saying right there. So the period of tangent and cotangent is pi. The formula to find the length of a period, I taught it to you as 2 pi over b, which is right for sine and cosine. But if you want to think about it more generally, it's the original period over b. That's the general formula for finding the length of the period. Original period over b. And for sine and cosine, the original period is 2 pi. For tangent and cotangent, it's 1 pi. So what does that mean? Well, it means that if you take the tangent of a value, or you take the tangent of that value plus any multiple of pi, you will get the same answer. Here's the tangent of 2. Okay, that's what you get. Now if I take the tangent of 2 and I add pi, same answer. What I'm basically doing by adding pi, let me go to my tangent graph and look at 2. Here's 2 in my tangent graph. Well, that's a height of 2. What did I get? Negative 2.18. So that's about negative 1, about right here. So what I'm looking at here is the answer in the first cycle. What I'm looking at here is the answer in the second cycle. The difference is this is pi units later. It's 1 cycle later. And if I add pi again, I would be on the graph right there. I would keep getting the same answer, just in different cycles, same y value. How about if I did tangent of 2 plus 13 pi? What would I get when I hit into there? Yeah,
The same thing?
same thing. This is the same answer. It's just 13 cycles later than the answer you were looking at. Okay. So that's what it means by adding pi n. N can be a negative number as well. N just stands for any integer. So if n is -5, we'd be subtracting 5 cycles, but it would still be the same answer. Now, what if I did something like tangent of 2 plus 1.5 pi? Nick, would I get the same answer there?
Say it again?
Would I get the same answer? How come?
Because it's another cycle.
Did I move another cycle by adding 1.5 pi?
Oh, no.
No, I didn't move an integer amount. You moved 1.5 cycles. So if you move 1.5, that's not a whole cycle, right? You're in the middle of the neck of a cycle, so you would not get the same answer. Right? You have to move 1 cycle, whole cycle. Right? It's got to be a whole cycle. How would I type in cotangent? Like, let's say I wanted the cotangent of 2. What would I put that in again?
Isn't it just second and tangent?
Second and tangent, that is inverse tangent. We haven't talked about that yet, but we will. No, we can't do second tangent. Yep.
1 over tangent?
Right. You have to do 1 over tangent. And that is how you do the cotangent. Okay, so transformations. There's no difference. They work exactly the same as the transformations we've done on everything all year. Okay, so I put up the template. I'm not going to really go through a ton of examples in depth with graphing tangent and cotangent. But let's just make sure we identify what letter does what. What kind of transformation is the A? What would that do? Yep. Yep, that's your horizontal shift, also known as a
Phase shift?
phase shift. How about B? What kind of transformation is that one? Yep.
Horizontal stretch or compression.
Yep, horizontal stretch and compression. And that's also known as a
Amplitude change.
no, B does not change the height of the graph. C does. Yep. That's a period change. C, we just said that, amplitude change. Amplitude change is also known as a,
Horizontal stretch.
nope, that's B. B is the horizontal stretch. When you're changing the amplitude, you're changing the height. So that's a vertical stretch. And then how about plus, could be plus or minus D. I didn't put both plus or minus. But what does D do? Yep.
Isn't it just a vertical asymptote?
No, D's not a vertical
It's a
asymptote.
vertical shift.
Vertical shift.
Oh.
Yeah. Should say shift. So those are your 4 different transformations. If B or C is negative, you can get a reflection. And depending on how you reflect tangent, you could make tangent look like cotangent. Because the only difference is the way the curve goes. Tangent, cotangent. So if you do a reflection, you could get that graph. So if I just gave you a picture of a graph and I didn't say what it was, it could be hard to figure out if it's tangent or cotangent. Especially if I said I could have done anything to it. I could have reflected it, shifted it. You might not necessarily know what graph I started with. Same with sine and cosine. Okay, so again, the formula that you want to remember for finding the period now, think of it as t equals original period divided by b. Whatever the original period is, we're going to divide that by b. So for tangent and cotangent, it's pi. Tangent and cotangent are the only two that use pi. Every other trig function uses 2 pi. The sine, the cosine, the secant, and the cosecant. All right, so we know that, if I go back here, we've got the first couple asymptotes for cotangent, and I wrote down the first couple asymptotes for tangent. Well, if we shift or stretch or compress horizontally, all of these asymptotes are going to change. They're not going to stay where they are. Right? If you shift left and right, they move left and right. Or if you stretch or compress, they could also change. So what I'm going to do now is show you how you can figure out what the new asymptotes are. And this is going to apply to any trig function. I've only shown you tangent and cotangent so far today, but secant and cosecant also have asymptotes. And what I'm about to show you works for those as well. So the first step to finding the new asymptotes, if you transform a graph, is find the original asymptotes. How many of the original asymptotes? Just the asymptotes in one cycle. That's all you need. So you're going to find all the asymptotes in one cycle. And then we're going to set up an equation. We're going to set each of those asymptotes equal to the argument and then solve. Okay, so what does that mean? Well, so you have this. The argument there is 2x. If you were trying to find the new asymptotes for tangent, I would start by finding the asymptotes, the original asymptotes. Original asymptotes for tangent start at pi over 2. That's the very first asymptote that's positive. So I would figure that out first, pi over 2. And then I would take that pi over 2 and set it equal to 2x, like this. What this equation is going to tell me is where this one asymptote is going to move to. What would x equal if I solved that for x? Yeah, pi over 4. Now, that's not all the asymptotes. That's just telling me where this one asymptote moved to. It moved to pi over 4. And that should hopefully make sense, because when you put a 2 in front of the x, what does this 2 cause the graph to do? Yeah.
It gets compressed by like a factor of 2.
Right. Everything gets compressed. Think about the origin as kind of the middle. Everything shrinks in towards the origin. Everything left and right of it gets compressed towards it. Well, if you had something out at pi over 2, and you compress that by a factor of 2, it's now at pi over 4. That's exactly what happened to it. So once you know where the original asymptote moves to, then you just have to tell me that that asymptote repeats every cycle. And how do you say that something repeats every cycle? You do something like this. You put plus the period times n. Okay, and this number x1, that's the number that you got right here in step 2. So by putting pi over 4 plus, remember the formula to find the period for tangent is pi over b, and my b value was a 2. So by writing this down, you've explained to me where every single asymptote is. The first one is at pi over 4, and then you can add any multiple of pi over 2 to that. If you think of it in degrees, the first asymptote is at 45, and you can add any multiple of 90 to 45, and you'll get another asymptote. And technically it's add or subtract, because if n was a negative number, you could find asymptotes to the left. If n's a positive number, you're finding asymptotes to the right. So I think the hardest part of that is really this step. You need to know the original asymptotes. And you'll have to know them for tangent, cotangent, secant, and cosecant. Okay, so I'm going to make a table in a little bit. And that'll help with step 1. Well, this is kind of the one I just did. So find the period of tangent 2x, and then we'll do a viewing rectangle that shows 3 cycles. Okay. How about, Evan, what's the formula to find the period of a tangent function? Anyone help him out? What's the formula, G?
T equals pi over b.
Yeah, t equals pi over b. It's the original period over b. That's the general formula for everything. The original period for tangent is pi, and what's b in this case? 2. There you go. This question doesn't ask anything about asymptotes, so I don't have to describe anything with that. They just said find the period and then show 3 full cycles. Okay. So if one cycle is pi over 2, how long is 3 cycles? Yep.
3 pi over 2.
3 pi over 2. So when I set my window, could you give me an x min and an x max that have a distance of each other, from each other, of 3 pi over 2?
0 and 3 pi over 2.
Yeah. The distance from 0 to 3 pi over 2 is definitely 3 pi over 2. Yeah. So that'll show me exactly 3 cycles. How come I don't have to worry about my y min and max as much? With sine and cosine, we definitely had to think about that. Why not with tangent and cotangent? Yeah?
The approach is infinite.
Right. Yeah, they approach infinity and negative infinity. So that's probably good enough. -5 to 5. Okay, put in your graph, tangent 2x. And if we did it right, we should see exactly 3 cycles. Emma, is that 3 cycles?
No.
No? How come?
Because you're only saying half of the last one and half of the first one.
Okay, so if that's a half and that's a half, together, what do those create?
I mean, it creates a third one.
It does create a
But
third
aren't
one.
they separate ones?
But that's okay. Yep. So the way we did this, we broke a cycle into pieces, but that's technically, it didn't say you couldn't. So that's a half cycle, whole cycle, half cycle. So technically, you have shown 3 full cycles. All right. Any questions on that? If you didn't want to break it into pieces like that, you would have to adjust your window so that the left edge is at the first asymptote. Okay? And we know the first asymptote, actually I already found that when I was just doing this sample problem right here. The first asymptote is at pi over 4. So if you had set your left edge to that, pi over 4, you could do that. But remember, to show 3 cycles, you have to travel a distance of 4.71 or 3 pi over 2 units. So you could do pi over 4 plus 3 pi over 2. Now this should show exactly 3 cycles, and I didn't break them up. Any questions on how I did that? I just figured out what my first asymptote was, and I made that the left edge of my screen. And then I just made sure x max was the amount of distance I had to travel for 3 cycles. Okay, so I like that graph better because it doesn't break it into pieces. But technically there was nothing wrong with this one. It's okay. All right, let's look at this one. So we have 2 graphs here. One of them is the graph of 2 tangent x. The other one is the graph of 5 tangent x. I want to know which one is which. Anybody think they can tell me which one is which? The windows are the same on both. There's no change. Same window. Yeah.
2 tangent x is the one to the right, and then 5 tangent x is the one to the left.
Yep. This is the 5 tan x, and this is the 2 tan x. How come? Can you explain why?
Because the 5 is bigger than the 2, so it'd be like more of a vertical stretch.
Right. Okay. This is what tangent normally looks like. If you take a graph like that and you stretch it vertically, that curve in the middle is going to start to get smoother. It's going to be less pronounced. So take a graph like that, stretch it vertically. I mean, I'm not going to say it straightens out completely, but definitely the curve starts to become less sharp. Versus if you take a graph like that and then you compress it, then the curve starts to become very exaggerated. Okay, so this requires that you know what the 2 and the 5 are actually doing. Any questions on? No. Okay. Let's see. All right, so let's take a look at secant and cosecant. So secant and cosecant are also periodic, meaning that they have a pattern that repeats over and over. But let's think about what secant is. How can you write secant in terms of like sines and cosines? What is secant? Yep.
Isn't that 1 over sine?
That's cosecant. So 1 over sine is the cosecant. And what about secant? Yep.
1 over cosine.
It's 1 over cosine. When you rewrite those 2 trig functions as fractions like that, it should become more apparent that these kind of graphs are going to have what in them? Yeah?
Vertical asymptote.
Yeah, they have to have vertical asymptotes again. Secant is going to have a vertical asymptote everywhere cosine is 0. And cosecant has a vertical asymptote everywhere sine is 0. So where is sine 0? 0, pi, 2 pi, 3 pi, and so on. So I have an asymptote at 0, pi, 2 pi, and so on. And that's what cosecant looks like. Now, secant looks similar, but all the asymptotes are shifted. So the asymptotes here are wherever the cosine was 0. So your first asymptote, pi over 2, 3 pi over 2, 5 pi over 2. Actually, maybe I labeled these on the bottom. No, not really. So anyway, but those are where your asymptotes are. So are secant and cosecant continuous functions? Marin, are they continuous functions? No. To be continuous, that means you have to be able to draw it without ever lifting your pencil. There's no asymptotes, breaks, or holes in it. These have an infinite amount of asymptotes, so definitely not continuous. What does a cycle look like? Well, let me draw a box. And I'll show you exactly what one cycle looks like. Okay, so one cycle is what's in that box. It's basically one U shape and one N shape. Now, if I number the asymptotes, we'll call this asymptote 1, 2, 3, 4. Which asymptotes, or how many asymptotes do you think belong to that black box? We've got to pick a number so that if I put in another box, that box could also have the same amount. Yep. 2. There are 2, yes. Secant and cosecant have 2 asymptotes per cycle. We could say asymptotes 1 and 2 belong to the box. Asymptotes 3 and 4 would be the next cycle. Okay. And it's the same for secant. Okay. Don't need to memorize all of them. All you have to do is memorize the asymptotes in one cycle, and then you automatically know all of them because they repeat regularly. All right. Now, looking at the box that I just drew on cosecant, what's the width of that box? Yeah, 2 pi. 2 pi. So because that box represents one cycle, and the width of that box is 2 pi, that means secant and cosecant have a cycle of 2 pi. It's exactly the same as sine and cosine. So sine, cosine, secant, and cosecant all have a natural cycle of 2 pi. Tangent and cotangent are the only ones that don't. They have a cycle of what? Yep. Pi. Yep. Okay, so because they have a cycle of natural cycle of 2 pi, the period formula is the same as what you were used to using for sine and cosine. It's 2 pi over b. I never give you a negative value for b, but if I did, remember, the period is a measure of length. It's how long the graph has to go before it repeats. You should never give me a negative number for period. You should also never give me a negative number for amplitude. Those are always positive values. So technically, if b was a negative, and it's not just for secant and cosecant, this is for any trig function, you never want to use b as a negative value if you are plugging it into this formula. If you are graphing it, yes, you do need to use the negative because it causes a reflection. So this table, it summarizes all the asymptotes we looked at. what it gives you is the first set of asymptotes that are positive in the first cycle. So we'll just go back and look at tangent and cotangent real quick. So the first asymptote that you get for tangent is pi over 2, and that's the only one that's in the first cycle. The first asymptote you get for cotangent that's not negative is 0. First asymptote is right at 0. When we look at secant and cosecant, the first set of asymptotes in the first cycle are pi over 2 and 3 pi over 2. And for cosecant, the first set of asymptotes that are in the first cycle are 0 and pi. Not 2 pi, that's in the next cycle. Just 0 and pi. So that's where all of these numbers are coming from. Okay, so there's your originals. And then how do you find the new ones? Well, that's what I explained a few slides earlier. This new value comes from this slide right here. That's how you find the new value. You have to do that. All I'm really explaining here in the new column is that tangent and cotangent always have one asymptote per cycle. Secant and cosecant have 2 per cycle. All right, so let's try looking at secant and finding the domain, range, period, and asymptotes. It's kind of like what we did yesterday. We did domain, range, period, but we did amplitude. These graphs don't really have amplitude because they go up and down forever. So amplitude is a characteristic that's only really talked about with sine and cosine. Okay, so domain, range, period, asymptotes. Okay, let's start with the period. What's the formula to find the period of a secant function? Yeah.
2 pi over
Yeah, and this is just basic secant. I'm not doing any transformations at all. So it's just 2 pi over 1 or 2 pi. You always want to find the period first because to describe asymptotes, you need the period. So do the period first. Okay, the range. Let's go back and look at the graph and see if we can figure out the range of secant. Zoom in so you can see it better. What does it look like the range is for secant? Yeah. Pi? Well, how come?
Oh, the range?
The range, yeah.
I'll tell you about the period.
Oh, the period. Okay, so we'll get back to the period in a little bit. We already got the period, right? That's what we got right here. That's 2 pi. So period is 2 pi. But what's the range of that? Yeah.
Is it negative infinity to negative 1 and then 1 to positive infinity?
Yeah, it's like everything that the range of sine and cosine isn't. Sine and cosine is negative 1 to 1. This is everything except negative 1 to 1. So it's from negative 1 down and from 1 up. So there's a gap in the middle. Secants and cosecants always have a gap right in the middle. You can change that gap if you stretch or compress, but you will always have a gap. All right, so The range is from -1 and down. And if you're not sure if you hit -1, you can always double check it by typing it in. Secant. Let's do 1 over cosine. Do zoom 7. And let's calculate the maximum. If we get 1, then we know we hit 1. If we don't, then I should have put a parenthesis. So let's do second calc maximum. Go here, there, and there. And I do actually hit -1, and that happens at a value of -pi in that particular cycle. So -1 should have a bracket. Same with +1. You could calculate the minimum, but it'll come out to 1. So, okay, so there's your range. Okay, asymptotes. What are the first 2 asymptotes in the first cycle of secant? Lens?
Pi over 2 and 3 pi over 2.
And did we do any transformations to them in this one? Nope. So because we didn't do any transformations, I don't have to go through any of this. If we did, I'd be doing all of that right now, which you just did step 1 for me. Find all the asymptotes in the original function, but you're done. So original function is pi over 2 and 3 pi over 2. And because they're asymptotes, you should put x equals. Now, if you put that, all you've done is tell me 2 asymptotes. I want to know all the asymptotes. What do I have to put on the end of each one of those to indicate they repeat forever? Yeah?
Plus pi over 2 then.
So we've got to put something like that. Did we find this already? What did we get for that?
Plus 2 pi then?
Plus 2 pi n. Yep. Now, that's not an elegant way to write the asymptotes. It is correct. But you could combine these into one statement. And that's what the book usually does. It's okay to write them separately like that. It's okay. And now the domain, what we generally say for domain is it's all reals except the asymptotes. That's the best way we can write it. So I'm not going to do 4. 4 is almost the same as 3. Example 4 has the same range, same period. The only difference is the asymptotes. Instead of putting a pi over 2 and a 3 pi over 2, you would put a 0 and a pi. That's the only difference between secant and cosecant. All right, so find the period and asymptotes and show a graph of 2 periods. Okay. What's the formula for the period of cosecant? Yeah.
2 pi over b.
And what's b in this case?
3.
Yep. So there's your cycle length, 2 pi over 3. Asymptotes. How many asymptotes does cosecant have per cycle? Yep, 2. So I'm going to need an x equals and an x equals. And the first 2 asymptotes for cosecant are 0 and pi. But I'm changing them. So now I need to set each of those asymptotes equal to the argument and solve. What's the argument in this problem? Raj? 3x. So off to the side, I'm going to set each of the original asymptotes from the table equal to 3x, and we're going to solve for x. The asymptote at 0, nothing happens to it, because when you do a horizontal stretch or compression, everything is compressing in towards the y-axis. Well, if you already have something on the y-axis and you compress towards it, it stays right where it is. So the first asymptote is still at 0. But the second asymptote is no longer at pi. It's been compressed in 3 times as much. So we have 0, pi over 3. And what do I put on the end of each one of them to indicate that they keep repeating forever? Yeah? The period, 2 pi over 3 times n. And yes, you really don't need the 0 there. You could just say for the top one, x equals 2 pi over 3n. And the bottom one is pi over 3 plus 2 pi over 3n. So you could eliminate the 0. So there's your asymptotes. And there's your period. I'm not going to graph it on the calculator. Okay. So the last thing is basically what we did yesterday, is solving a calculator type problem. But the way I want you to write your answer today is if they don't say to solve in a specific window, like that question right there. It says find all solutions. That means you need to put plus the period times n on the end of your solution to indicate to me that it keeps repeating. That's what you didn't do in the homework last night. Okay, so remember, if you can find one solution, that solution is going to repeat every cycle. So the idea is find all the solutions in one cycle. Did I write that anywhere? And then do plus the period times n on each one of them. So let's start by finding the period. They didn't ask for it, but you're not going to be able to write the answers without it. What's the period of cosecant if you don't do anything to it? Yeah?
2 pi.
2 pi. So I already know on the end of every answer that I find in one cycle, I need a plus 2 pi n. Okay, I don't have a button for cosecant, so I need to type it in as 1 over sine. Just like that. You're going to put in negative 1.6 on y2, and you're going to set your screen to 1 cycle. You only want to find the answers in 1 cycle. Let's go 0 to 2 pi. Could you go 2 pi to 4 pi? Technically, you could do any cycle you wanted. You just have to find all the answers in 1 cycle. That's how I usually do it. 0 to 2 pi, or 0 to whatever I need. Okay, so if I did this right, 1 cycle should be a U shape and an N shape. How many answers do I get per cycle? Travis? 2. So we're going to have first answer, second answer. Whatever I get for the first answer, I know that it will repeat every cycle. The second answer will also repeat every cycle. If you don't put the plus 2 pi in, you haven't done this. You will have found specific answers, not all answers. Okay. So now let's find the first two. Second calc intersect. You do have to be a little careful. You've got to get your cursor on this bottom part. That now it's okay. So 3.82. And the other answer, we'll just move the cursor a little bit. 5.61. Okay, so last night you just wrote 3.82 and 5.61. Tonight you're going to just put plus 2 pi in. Okay, so secant and cosecant generally will have 2 answers per cycle, because when you draw a horizontal line, it's usually going to hit twice. The only way it could hit once is if it was right at -1 or right at +1. Then it could hit once. Right, and finish up with this one. Tangent x equals 2.5. What's the period of tangent? Just regular tangent. Yep, pi. So I'm going to set my cycle 0 to pi. I'm going to put in tangent x, and I'm going to put in 2.5. Now, tangent or cotangent, generally, I broke the cycle in half. That's fine. That is a cycle of tangent, though. It's just half and half. It generally will only hit the graph once. So we're going to get second calc intersect. Okay, that's what happens if you don't put your cursor in the right spot. You do have to be a little bit careful. Now it's okay. So the first answer is 1.19, and that'll repeat every cycle. You can add or subtract 3.14 as many times as you want to that number, and you'll get another answer earlier or later in the cycles. Okay, so that's all the other trig functions. Notice we don't do a lot of sketching by hand. It's more solving equations and describing the period, asymptotes, things like that. All right, so those are the questions for tonight on 352. We'll take a look at them tomorrow. And then the rest of the week, we're going to be doing section 6.5, which we're going to split into 2 days, and it is totally different. Nothing to do with graphing. We're going to be looking, I think, at right triangles, like opposite, adjacent, hypotenuse, stuff like that.